Hello everyone, I hope you all are doing well. Today I am going to discuss about the topic convergence of Fourier series. This is the I think ninth video on this topic of Fourier series. Before coming to the theorem of this convergence Fourier series, uh, let me show you one simplest example, and from there step by step we will try to understand the what is convergence theorem and what is its importance. Okay, so let one example take one example that fx is equal to x, and it is defined from minus pi to pi. Okay, so we can plot this thing like uh, this way. This is the function. It is suppose minus pi to pi. Okay, so since it is an odd function, and it is an odd function because this plot, it is symmetric about the origin. Okay, so these things were already discussed in the video where I discuss about the odd and even functions. So since it is an odd function, there will be no coefficients an and a0. A0 and an will be 0 here. So we have to find only the bn. So series will be a sine series. So if you find this series, Fourier series here, it will be like, I have skipped this in between steps. Okay, it will be like minus 1 to the power n plus 1 n sine nx. Okay, so this is the series. So if we expand to few terms, and then putting n is equal to 1 here, sine x 1 minus sine 2x 2 plus sine thrice x 3. Okay, it will go up to infinity like this. So now let us check the summation of this infinite series at the value x is equal to 0. Okay, so this is the point where x is equal to 0. So if this infinite series is having some finite value at that particular point, then we can say that this Fourier series is converged. Okay, at that point. Okay, so put this value, it will come 0 minus 0 plus 0, and it will, all terms will be 0, so definitely summation will be 0. Okay, so since we are putting x equal to 0 in the right side, so left hand side also we can put. So when we put in the left hand side means at the function itself, so it will giving the function value 0, means the both this series which is converges to 0 at the value x equal to 0, so that will be also given by the function itself. Okay, so here left hand side is equal to right hand side. Okay, so let us check at another point. Same thing, means we are going to check the convergence of this Fourier series at another point, that is x equal to pi. Where? This point, x equal to pi. Okay, this point. So now let me erase this part first. We have already checked at x equal to 0, and we have seen that minute. Okay, it is not removing. Okay, let's see, check at x equal to pi. Sorry, at x equal to pi. Okay, so if you put the x equal to pi in the summation, then sin n pi 0, sin 2n pi 0, sine 2 pi 0, sine pi 0, all terms will become 0. So as a result it will give 0. Okay, so but if you put in the left hand side, if you put in the function x in place of x, if we put pi, so it is not, it is giving pi, not giving 0. Okay, so definitely the series which is converges to 0 is not given by the function itself when we put the x equal to pi in the function. So here it is not happening, same thing is not happening like in the previous case. So left hand side and right hand side not both are equal, so there is a problem. Okay, so what is the problem? So to understand that thing we have to know the convergence theorem. So I think you have understood what I am trying to mean by this problem. Okay, so means at all points it is not equal, means the series which is converged to some value, it is not shown given by the function itself in the left hand side. So what is the problem? That thing we are going to discuss. So let me write the theorem now. Okay, if fx is a piecewise smooth function, smooth function uh, defined in the interval minus pi to pi, it has a Fourier. Okay, here it should be periodic. Okay, periodic, what we need should not forget, we should not forget, it has a Fourier series, and the in the series converges to, means if fx is a periodic function which is piecewise smooth, defined in the interval from minus pi to pi. So remember, it is not necessary that it will be always given from minus pi to pi. Here I am taking the variable as an angle, therefore I am mentioning this interval. So it can be from minus L to L also, or it can be from 0 to twice L, from 0 to twice pi, like that way also. Okay, so it has a Fourier series. So piecewise a smooth function, for the time being you remember, piecewise smooth function are function which are piecewise continuous. Okay, suppose fx, it is a piecewise continuous, and if its derivative f dash x, that is also piecewise continuous. So those type of functions are called piecewise smooth function. So I will make one video regarding the piecewise smooth function and why piecewise smooth function is necessary for its Fourier representation of a function. Okay, those things I'll make one video again. But now you remember the function, we remember about the Dirichlet condition, the function which satisfy the Dirichlet condition, and those function can be expressed as a Fourier series, and the series and that Fourier series converges to one, converges to the function fx. Okay, now we are talking about that Fourier series which converges to function fx when x is a point of continuity. Okay, so okay, I will again make you understood what is this. First write down the theorem. 2 average of right hand side and left hand side limit. Okay, when x is a point of discontinuity. Okay, then another point is there too. To this value when x is n point, when x is a n point. Okay, like x equal to pi plus pi or x equal to minus pi. So what is this? So okay, so let me write the Fourier series, the general expression of Fourier series. We know if the periodic function is fx, so we can write the Fourier series of this function as this is the general expression of Fourier series. Okay, cos nx plus bn sin nx. Okay, so what I am telling here, so if we are uh, we are talking about a point, suppose x. Okay, so here I have not mentioned any point, particular point. So suppose x equal to x naught is a point, like in the previous example where we observed that x equal to 0 is a point. Okay, so suppose it was particular example, but here in general way I am writing, suppose x equal to x naught is a point where the function is continuous. Okay, where this function is continuous, this function, then the Fourier series at that point, Fourier series at that point. So if you put x equal to x naught here, x equal to x naught here, then Fourier series at that point is converged to the function itself. Okay, because in the previous example we have seen that when x equal is 0, which is a point of continuity, in that point when you put the value of x equal to 0 in the function, that function value was giving the value of the summation, means our Fourier series was converged to that function value at x equal to 0. Okay, that is the thing that is written by this point. But when this x is equal to x naught is not a point of continuity, it is a point of discontinuity. So in that case we cannot simply write that we cannot simply put the x equal to x naught in that function. Okay, so in that case we have to take the average of left hand side and right hand side limit. Okay, so okay, we'll try to understand these things now. Let me plot that curve again. Okay, okay, so um, that function I am again plotting x equal to 0. Here it is pi, here it is minus pi. Okay, so to understand the convergence theorem, it is also important to talk about the periodic extension. Okay, so I will come to this thing again. Let me first plot the periodic extension of this function. It will be like this. Okay, so here pi, here it will be thrice pi, here it will be 5 pi. Okay, so suppose when we write some uh, function in terms of its Fourier series, function means periodic function in terms of its Fourier series, then we find the coefficients a n and bn with the help of the function defining in a for particular interval. Okay, that thing already we discussed. But now this Fourier series, it is uh, representing the function after the periodic extension also. Okay, it is not now constrained to this region. This Fourier series is now representing the fx at any point, here also, all points. Okay, so now this fx This fx is a function after periodic extension. In some books, if you can find that this after periodic extension, they used capital Fx to representing the function after periodic extension. But here we are saying that it is function fx is now representing the function after periodic extension, because there will be no any change in the function value. Suppose fx equal to x, it will be after periodic extension also it will be fx equal to x, as function fx plus twice pi is equal to fx. That is the condition of periodicity. Okay, so now this fx, it is representing the function after periodic extension also. Okay, so I hope it is clear to you. So this thing is very important in understanding the convergence of Fourier series, because here we are going to discuss about the convergence of Fourier series at the point of continuity and at the point of discontinuity and at the point of endpoints. Okay, therefore it is important. So in that previous example, where was the problem happening? Problem was happening at x equal to pi. Okay, here at x equal to pi. So now see, this x is equal to pi. Now we are talking about this function. Okay, after periodic extension. So when x is equal to pi, there is a discontinuity. Suddenly it is coming here, so there is a jump discontinuity. Jump discontinuity. So when there is a discontinuity, in that case, Fourier series, this does not simply converge to fx. So it will converge to this value that was written there, that average of x naught minus average of this right hand side and left hand side limit we have to take. So here x equal to x naught, here what is the value of x naught? Here it is the value. Okay, it is, if you see, this is the pi, x equal to pi. Okay, here we are now talking about the convergence of this function of this Fourier series at x equal to pi. That is the point of discontinuity. So here you have to take here this x pi. Okay, so here in place of x naught you have to put pi minus pi plus. Pi minus and pi plus means if you approach this point from the negative direction, like from this way. Okay, so what will be the value of this function? It will be pi. It will be pi. Okay, so if you approach this point, this x equal to uh, pi, this point, from the positive direction, then it will reach this point from the positive direction. It is coming like this way, this point, that is x, that is minus pi. Okay, so it will give now 0. So earlier we observed that x equal to pi, if series was converged to 0, and the function was not giving 0, but now if we apply this formula, then it is showing that it is 0. Okay, so at the point of discontinuity, we have to use this relation to find the value of convergence. Okay, so I think it is clear to you, that second point. Now another point is there, that is the end point. And very interestingly, in this function, the endpoint at that point of discontinuity, it both to become same. So but it is not always happening like this way. Okay, so uh, so uh, so um, let me show you another example. Suppose fx equal to minus 1 from minus pi to 0, fx equal to 1 from 0 to pi. How it will plot? How will you plot this function? It is minus 1, it is plus 1. Okay, so minus 2 plus, this is x equal to 0, x equal to 0, this one. So this is a odd function. Now if you see, it is symmetric about the origin. So here also you need not to find the value of a naught and an, but here I am not going to derive the Fourier series, okay, all these things, but I am showing this example to show the point of discontinuity and point of endpoints. Okay, so here x is equal to 0, it is a point of discontinuity. Okay, so here if you find the Fourier convergence of Fourier series, then at x is equal to 0 you have to use this relation again. F 0 negative means coming from negative direction, f0 coming from positive direction. If you find the convergence or summation of the Fourier series, then in the function you have to approach like this way. So in this point you will find, okay, and definitely it will come 0, because it is if you come this point of negative direction, minus 1, then it is plus 1, so it will give 0 definitely. So it is the example of point of discontinuity. But what is happening here at x equal to pi, x equal to pi, okay, and x equal to minus pi. Okay, so here x equal to pi and x equal to minus pi, pi are uh, endpoints. Okay, and remember, if you do the periodic extension of this function, so it will be look like this, is not it? So since x equal to pi, that is the endpoint itself is also a point of discontinuity, and endpoints are point of discontinuity in this case. In the earlier example also we have seen, but remember, always endpoints are not point of discontinuity. Okay, so therefore we are going to find a relation regarding the convergence of Fourier series at endpoints, irrespective of the endpoints discontinuity or continuity. We can use that relation always. So that thing we will check. So now see, now regarding endpoints, we are now talking about the convergence of Fourier series at endpoints. But these endpoints, this is also a point of discontinuity, so we can simply use that relation at endpoints minus plus. Okay, so here it is a point of discontinuity. If you approach this point from negative direction, this is the value of that limit, and if we approach this point from in this direction, this is the value. Okay, so now this can be written like this. If you see f minus f pi minus, okay, f pi minus means this point. Okay, so simply write this thing. Then f pi minus plus means this point. So if you reach this point, the value at this point is function value, and at this point the value of the function at this point, this is both are similar. Okay, so here therefore we can write, here also you have to coming from the positive direction. So here you can write, so in place of pi plus minus pi plus we can write. Okay, so at the endpoints we are trying to show the this relation in terms of the uh, in a one interval we are showing this thing. Here it is the minus pi, here it is the pi. Okay, and if you find that the convergence value, you will see that at x is equal to plus minus pi means at the both points, both endpoints, the series this will give the same value. Okay, means Fourier series will converge to the same value at the endpoints. At the plus and minus at both points, it will converge to the same value. Okay, uh, that is the thing. So now another point is that here it was not observed that these endpoints are uh, continuous. Here endpoints, here we have seen that endpoints are also having one point of this, it is a point of discontinuity. So sometime what happens, suppose I am drawing this function, suppose this is f(x) equal to x square, this is a function. Okay, this is a even function. If you do the periodic extension, if you do the periodic extension, it will be look like this. Okay, so x equal to 0, x equal to pi. So here x equal to pi after periodic extension, this is not a point of discontinuity because it is continuous here due to periodic extension. But even though we can use this relation to find the convergence of Fourier series at that point. Okay, so always remember it is continuous or discontinuous. Endpoints, sometimes we obtain endpoints as a point of continuity, and sometimes as a endpoint of point of discontinuity. Okay, so it does not depend continuity or discontinuity endpoints. We have to always use this relation to find the convergence of Fourier series at endpoints. Okay, you remember this thing. So, and other thing we have already observed that at the point of discontinuity, you have to take the average of left hand side and right hand side limit at that point. Okay. So when we solve some problem related to this topic, then this uh, this thing will be uh, clear to you. Okay, so I hope you have got some idea regarding the convergence theorem. So any doubt, any questions, you can ask me in the comment section. Okay, and thank you.